In this video, we're going to talk about the F distribution. So suppose that W1 and W2 are independent random variables and they have chi-squared distributions with nu1 and nu2 degrees of freedom. I'm just going to call them V1 and V2. I think it should be nu1 and nu2, but V1 and V2 degrees of freedom, respectively. So W1 is a chi-squared distribution with V1 degrees of freedom. W2 is a chi-squared distribution with V2 degrees of freedom. And W1 and W2 are independent. So if you have the random variable, which is defined to be W1 divided by V1 divided by W2 divided by V2, this is said to have the F distribution. And in this video, we're going to calculate, we will find the density function of X. So recall that for the chi-squared distribution with V degrees of freedom, we have F of Y equals Y to the V over 2 minus 1 times E to the minus Y over 2 divided by 2 to the V over 2 times gamma of V over 2. So this is the chi-squared distribution. This is the density function of a chi-squared distribution with V degrees of freedom. Okay, so W1 and W2 have chi-squared distributions, and when you have, so W1 has a chi-squared distribution, and then if you take a constant times W1, so W1 over V1 is just 1 over V1 times W1, this has density G of Y, which is F of V1Y times V1. This is from the formula for the density of a function of a random variable. So you have this function which is 1 over V1 times W, and then the inverse is V1 times X. Right? You're just multiplying by V1, and then there's a theorem that says that the density function is you take F of V1 times Y and then multiply by the derivative of that function. So the derivative of V1 times X is just V1, so that explains the times V1. Okay, so that means that W1 over V1 has density, I'm just going to write it, it's V1 times F of V1 times Y, right? So it's times Y to the, it's V1 times Y raised to the V1 over 2 minus 1 times E to the minus V1 Y over 2 all over 2 to the V1 over 2 times gamma of V1 over 2. And similarly, W2 over V2 has density So let's call this, say, f1 of y instead of g of, or well, we could just call it g1 of y, sure. Has density g2 of y, which is v2 times v2y to the v2 over 2 minus 1 times e to the minus v2y over 2, all over 2 to the v2 over 2 times gamma of v2 over 2. And now there's a formula, so if w1 and w2 are independent, then w1 over v1 and w2 over v2 are independent. So independent because w1 and w2 are independent. So I have a quotient of two independent random variables, and now I can use the formula for the density of a quotient of two independent random variables. So by the formula for the density function of the quotient of two independent random variables, we have that the density function of w1 over v1 over w2 over v2, so as a function of z, it's defined to be the integral of the absolute value of y times f1 of y, f2 of yz. Oh, I guess in this case g1 and g2, so I'm just using different notation. Oops. Integrated with respect to y. Okay. And for this, for the chi-square distribution, y is going from 0 to infinity. So this is going to be the integral from 0 to infinity. Now the absolute value of y is just y, so it's going to be, because y is positive. So it's y times, now I substitute what I have in, v1y to the v1 over 2 minus 1 times e to the minus v1y over 2 over 2 to the v1 over 2 times gamma of v1 over 2 times, and now I have my g2, but I plug in yz, right? So times v2yz to the v2 over 2 minus 1 times times e to the minus v2yz over 2 over 2 to the v2 over 2 times gamma of v2 over 2 dy. So now I'm going to move the constants out. I also have v1, v2. The v1, v2 is from, where is it? Yeah, I just have this v1, v2, that v1, and that v2. I just moved it out. Okay. But now I'm ready to move everything out that is independent of y because I'm integrating with respect to y. So the things I'm going to move out are going to be the denominators, right? There's no y here. I'm also going to distribute the inside of in the parentheses in the numerator. So when I do that, I'm going to get v1, v2, and then I'm going to get times v1 to the v1 over 2 minus 1 times v2 to the v2 over 2 minus 1, and then divided by 2 to the v1 over 2 times 2 to the v2 over 2. I'm just going to combine that, v1 plus v2 over 2, and then times gamma of v1 over 2 times gamma of v2 over 2. So that's the constant, and then I have the integral from 0 to infinity of y times y to the v1 over 2 minus 1 times, and then I have a yz. So I have a y to the v2 over 2 minus 1. Oh yeah, and I have a z to the v2 over 2 minus 1. So I should move that out also. Z to the v2 over 2 minus 1. And then I have those two e terms that I multiply. So it's going to be e to the minus, and then I can write it as v1 plus v2z times y over 2 dy. And now I have this product. This I can simplify to y to the v1 plus v2 over 2 minus 1. Right? Okay, so I have this constant. I have this constant here. I don't have to do anything about this, right? That's just going to be out, and I have to evaluate this integral. So to evaluate this integral from 0 to infinity of y raised to this power times e raised to this power basically what I want to do is I want to make a substitution, because I know that I have a gamma function when I have y to some power times e to the negative y. But right now I have this constant in front of the y. So I should use a u substitution. U equals v1 plus v2z over 2 times y. Right? Because that way I'm just going to get e to the negative u. So then I can use the formula for the gamma distribution. So when I do the substitution, I get du equals v1 plus v2y over 2 dy. Oh, no, there's a z here. Right? So dy is 2 over v1 plus v2z du. So this dy is going to turn into this. This part is just going to be negative u. And then y is equal to, so I'm going to get y equals 2 over v1 plus v2z u. So I'm going to use that and substitute for the y here. And when I evaluate the bounds of integration, they stay the same, 0 and infinity, right? Because if I substitute y equals 0, I get u equals 0, and then y equals infinity. Okay, it's just u equals a constant times y. So that other bound will still be infinity. So now I'm ready to do the substitution. I get the integral from 0 to infinity of 2 over v1 plus v2z u to the v1 plus v2 over 2 minus 1 times e to the negative u, and then I have this dy. So I have du and then 2 over v1 plus v2z. Okay, now I'm ready to evaluate the integral. So this 2 over v1 plus v2z, when I distribute it inside the parentheses, okay, and then multiply it by this 2 over v1 plus v2z on the outside, I'm going to get 2 over v1 plus v2z raised to the v1 plus v2 over 2 power, and then the integral from 0 to infinity of u to the v1 plus v2 over 2 minus 1 e to the negative u du. And this is where I can apply the gamma density, the gamma function. This is gamma of v1 plus v2 over 2. So that's the integral. Okay, so that's that integral, and then I just have to multiply it by this constant. So what is the f of z? Okay, so f of w1 over v1 over w2 over v2 of z is the constant v1. Okay, what was it? v1. Well, I can multiply the v1s together. I get v1 to the v1 over 2 times v2 to the v2 over 2 times z to the v2 over 2 minus 1, and then over 2 to the v1 plus v2 over 2 times gamma of v1 over 2 times gamma of v2 over 2. Is that right? Yep. And then times, okay, 2 to the v1 plus v2 over 2 over v1 plus v2 z to the v1 plus v2 over 2 times gamma of v1 plus v2 over 2. And then these powers of 2 will cancel. And I think that's the only thing that cancels. So what I'm going to be left with is v1 to the v1 over 2 times v2 to the v2 over 2 over gamma of v1 plus v2 over 2 times z to the v2 over 2 minus 1 times v1 plus v2 z to the v1 plus v2 over 2. So that is the density function of the F distribution. There might be other ways of writing it. So if you look in books for the F distribution, it will be written in a different way. But if you just do the algebra and simplify, you should get the same thing. Okay, so this F distribution, I mean, I wanted to do the calculation, but I think in practice, I don't think it's very applicable. You can just, in practice, you can just use the software if you wanted to do a test using the F distribution to calculate the p-values. Okay, thanks.